Hi, welcome to my channel, and today we will be looking at the relationship between the molar diffusion flux and the mass diffusion flux between of a certain component in a mixture of two gases. So here's the problem, and we'll be looking at it right now. So the setup for this problem is that we have a sealed container, which means that nothing goes in and nothing goes out of this container. And we have two gases, gas A and gas B. And uh, the volume occupied by both of these gases is exactly the same. So that means that there's a divider right in the middle of this container. And on one side, there's gas A, and on the other, there's gas B. And another thing to note is that gas A and gas B are both exerting equal amounts of pressure. So yeah, both of their pressures and volumes are equal. And in this problem, we'll be assuming that the temperature of this whole system stays constant. So yeah, before even we start solving this problem, what we need to know is a few terminologies. So we have molar flux, which I'll be represented by uppercase N, the mass flux, which I'll be representing by lowercase n, the molar diffusion flux, which is represented by uppercase J, and lowercase j represents mass diffusion flux. Then we have molar concentration, which is C, and mass concentration, which is rho. And then we have Y, which is the molar fraction. And then we have VI, the average velocity, average mass velocity of a certain component, and VI bar, which is the average molar velocity of a certain component. So yeah, we see that there's a lot of fluxes in these terminologies. So let's go right ahead and look at what a flux is. So basically what a flux is that if we have a certain container, for example, so we have a cubical container right here. So a flux is basically how much of a certain term passes through an area per unit time. So for example, if we have this particular area, let's call that A. I'll change the color of my pen. Right, so let's call that A. And if, like, for example, in this case, let's say a few molecules, the molecules. These molecules are passing through this area. So the rate at which these molecules pass through that area is basically a flux. So flux would basically be a certain term that passes through an area per unit time. So if we talk about molar flux, that's basically the total amount of substance, the total moles of a substance that passes through an area per unit time. Same for the mass, like the mass of a certain component that passes through an area in per unit time. So same thing goes for the diffusions as well. So yeah, now that that's out of the way, another thing that we need to use while explaining this relationship between molar diffusion flux and mass diffusion flux is that we need to establish that the molar flux of a component, the total molar flux is equal to the total concentration times the molar average velocity, the total molar average velocity. So let's see where this comes from. So we already know that the number of moles is equal to the concentration of a certain component. Let's make this I instead. So the total number of moles of a certain component is equal to the concentration of that component and the volume occupied by that component. To make it clear, I'm going to represent volume by V twiddle because we have a bunch of V's going around, so we don't want any confusion. So yeah, that's the number of moles of a substance. So if we want to convert this number of moles into a molar flux, we'll simply be dividing this term by the area and time. And this comes from this term right there. So that's basically the molar flux. So since we're dividing one side by area and time, we're going to have to do the same thing on the other side. So that's what we get. So we can write the whole term on the left-hand side as the molar flux of a component I, which is equal to concentration of I times, now the volume can be written as the product of area and length. So what I'm going to basically do is that replace VI with this area times this length right here. So that's basically the volume. So what we end up with is concentration times area times length divided by area times time. So we can see that these two things cancel out, so we get molar flux of component I is equal to concentration of I times the velocity of I. So yeah, that's for one component. So if we make a sum of all of the components in this mixture, we get the total molar flux equates to concentration times the total molar average velocity. So yeah, we're going to be using this relationship quite a few times in this while proving this relationship. So now, what we have is, let's start with what the molar flux of a certain component in a gas is. So what we can represent this as is so when there's a mixture of two gases, if we assume that these gases are uniformly distributed throughout the container, we can simply say that the molar flux of a certain component is simply equal to the mole fraction of that component times the total molar flux. So that's pretty understandable. However, in this particular case, we have two gases that are actually in the process of mixing, so they are not uniformly distributed. So another factor that comes into play while determining the molar flux would be the molar diffusion flux of that component. So in the process of mixing, the molar flux of a component is equal to the product of the total molar flux and the mole fraction of that component added with the molar diffusion flux of that component. So since we have gases A and B, I'm going to write this, and we're specifically looking at gas A, I'm going to write this as molar flux of component A, mole fraction of component A, and molar diffusion flux of component A. So in the same way, the mass flux of component A would be equal to the weight fraction, the mass fraction of component A times the total mass flux added with the mass diffusion flux of that component. So let's try to solve this. Like, let's see where we can go from here. So I'm going to solve the first equation here. So we can write the molar flux of component A as the concentration of A times the average velocity of component A. And this comes from here. Let's remove that. And another thing that we can do is write this term as the the total concentration times the molar average velocity, which also comes from right there. So let's keep trying to solve this thing. So where we go from here is that component concentration of A times average velocity of A is equal to, now, so we can see that the product of the mole fraction of A and the total concentration would simply be the concentration of A. So now this has been further simplified into this equation. Now we can see that we can move this term to the left-hand side and have concentration of A in common, and we can end up with a very simple final equation that can be written as the molar diffusion flux of A is equal to the concentration of A times average velocity of A subtracted by the total molar average velocity. So yeah, we have this equation now. So now we'll go ahead and do the same thing on the other side. So what we're going to do is the mass flux of A is simply equal to the density of A times the average velocity of A. And in the same way, the total molar flux, total mass flux is simply equal to the total density times the molar average mass average velocity added by the mass diffusion flux of A. So we're kind of doing the same thing here as well. We have this term, the mass fraction and the total density, which is simply equal to the density of component A. So let's replace that. Density of A times average velocity of A equals density of A times mass average velocity, total mass average velocity, added with the mass diffusion flux. So we'll do kind of the same thing, move things around, and we end up with a final equation, which is the mass diffusion flux of A is equal to the density of A times the velocity of A, average velocity of A, minus the mass average velocity. So now we end up with two different equations. So yeah, that's what we end up with. And to go further from here, we're gonna have to look at a specific situation. For example, let's say we have a closed tube, just as we did last time. And let's take a look at a certain area within this tube. So let's take a look at this particular area. So what we have here is that there's a bunch of gases mixing around, and we're taking a look at a certain part of that tube. And one thing to note is that this is still a closed system where the two ends are sealed. Oh, that's not how you spell sealed. There we go, sealed ends. What this means is that nothing can pass through here or here. And same goes for this side as well. Now, if we look at the molar flux of one side, say this is a thickness of delta X, right? So if we look at the molar flux at this point and assume it to be N, and then we look at the molar flux of this point and assume it to be N plus delta N, we're gonna have to say that N is actually equal to N plus delta N. Now, the reason behind this is that we know for a fact that the pressure in this vessel is constant. And since fluids exert pressure on all directions equally, they exert equal pressure in all directions, the pressure at every single point in this container has to be constant. So that means the pressure that exists here and the pressure that exists here has to be the same. So in order for that to happen, we know that by the gas law that PV equals nRT. This N is the number of moles, not to be confused with mass flux. So by this, we know that if pressure and volume are constant and divided by RT, we've already established that temperature is constant as well, and R is by itself a constant, a gas constant. So we know that total number of moles has to stay constant. And by that, what we can say is that since the number of moles is constant, the molar flux also need to be the same, like at all points in this container. So we end up with this observation that N is actually, delta N is actually 0. Let me erase that part real quickly. Okay. Now, another thing to note is if we look at the boundaries right there, the molar flux at the boundaries has to be equal to 0. And the reason behind it is that nothing is passing through. It means like no molecule is passing through the boundary. So since there's nothing passing through the boundary, and molar flux itself is a term that describes how much of something is passing through per area per time, the molar flux at the boundaries, both of these boundaries, has to equal 0. And we've already established that the molar flux at all points in this container has to be the same. So since the molar flux at the edge is equal to 0, it means that molar flux at every other point in this container also has to be 0. So we can say that in this container, the molar flux, the total molar flux is equal to 0 at all points. Now this is very interesting because we've already established another equation that N is equal to C times V, which is molar flux is equal to the total concentration times the total molar average velocity. So where we go from here is that we have this equation, CV. So yeah, we know that the total molar flux is 0, and we know that concentration can't be 0 because the container has fluids, it has substances, and by the definition of concentration, which is number of moles divided by volume, we know that number of moles is not 0, so concentration cannot be 0. So this tells us that the molar average velocity has to equal 0. And the reason behind it is C is non-zero. Now this is very interesting because we can plug this value right into this equation. And now we end up with the relationship that the molar diffusive flux of A is equal to concentration of A times velocity of A subtracted by 0. And this is simply written as CAVA. So yeah, our initial equation got simplified by quite a bit. Now, what we can write from here, now, if we take a look at this particular equation, we see that we have the velocity of A in that equation. So now we use this relationship to say that velocity of A is actually equal to the molar diffusion flux of A divided by the concentration of A. And we simply plug this value into this equation. And now what we end up with is that the mass flux of A is equal to the density of A times the molar diffusion flux of A divided by concentration of A minus the mass average velocity. So, okay, so let's go further and work with this equation. So now what we have, simply I'm going to multiply these things around. So what we have is density of A divided by concentration of A times the molar diffusive flux of A minus density of A times molar mass average velocity. Now, let's dissect this term right here and see what we end up with. So density of A is simply the mass of A divided by the volume of A. And the concentration of A is simply the moles of A divided by the volume of A. So the volume components both cancel out, and what we end up with is mass of A divided by moles of A. And we know that mass over moles is simply the molecular mass of A. So another simplification. So we can simply write this particular term as, okay, I didn't intend that to happen. Okay, there we go. So we write this term as molecular mass of A times the molar diffusive flux of A minus the density of A times volume. Okay, now let's see what more we can do with the equations that we have so far. Okay, let me erase these parts first, just to make it cleaner. Okay, now the mass average velocity of velocity. Now let's see what mass average velocity is. We know that the mass average velocity is simply the summation of the density of a component, times the velocity of that particular component. So in our case, in the case of this tube where there are only two gases, we can simply write this term as Yeah, so we can simply write velocity as the density of A. Oh, my bad. I actually forgot to include a term here. The mass average velocity, by definition, is actually the summation of the density of a component times its velocity divided by the total density. Yeah, so this is the actual formula for that. Okay, so if we look at our particular case, we can write that as density of A times velocity of A plus density of B times velocity of B divided by the total density. Okay, so let's see where we can go from here. We already noticed that the VA can be written as the velocity of A can be written as the molar diffusive flux of A divided by the concentration of A. So let's go ahead and write that right away. I'll bring out the density term outside just so it's easier to work with. Actually, I think I'm gonna need a little more space than this. So let's erase that. And okay, I'm gonna start working from this position now. All right, so what we have so far is molecular mass of A times the molar diffusion flux of A minus density of FA divided by the total density times density of A, and we replace the velocity, the average velocity of A by this term, and we get this plus density of B. So by the same logic that we ended up with this equation, we can say that this applies to VB as well. So we can write that as this term. So this is the molar diffusion flux of B divided by concentration of B. There we go. All right, let's see where we can go from here. So immediately we notice that we again got this particular term, which is right here, and we replaced with this. So we're going to do the same thing again. So just write everything we've already written down. So another thing, the total density of a substance divided by the total density of component A divided by the total density is simply the mass fraction of A. And the reason behind it, let me show you right away. Density of A divided by density is equal to, so density is simply the mass of A divided by the total volume, right? And then again, the total density is again total mass divided by total volume. So, okay, so the reason we didn't use the volume of A here is because we're looking at a gas. And when we look at a gas, we look at the container it's occupying for its volume, right? Since A and B are occupying the same volume, which is the container we have right there, we can say that its density is simply the mass of A divided by the density or the volume of the container. So these two terms simply cancel out, and mass of A divided by the total mass is simply the mass fraction of A. And that's where this thing comes from. Okay, so let's keep working on this. Now we have, so density of A divided by concentration of A, as I already mentioned, is simply the molecular mass of A multiplied by the molar diffusion flux of A plus, and same thing applies to this as well. This is simply the molecular mass of B times the molar diffusion flux of B. So our formulas have been a lot more simplified. So for one last thing, what we need to do is that I'm gonna say that the molar diffusion flux of A is actually equal and opposite to molar diffusion flux of B. So why am I suddenly giving out this relationship? Let's prove that. So I've already established that the molar flux, the total molar flux in the container is actually 0. So what that means is, and by definition of total molar flux, we can write it as the sum of molar flux of total molar flux of component A plus the molar flux of component B as 0. And what I can write now is molar flux of A is equal and opposite to molar flux of B. Okay, so what this suggests is that in the container, every molecule of A, I think I represented A as, okay, I believe I've represented A as a green. So let's do that again. So there's a green molecule of A, and I believe B was blue. Okay, so let's go with that. Right. So what this equation essentially says is that for every molecule of A that moves this direction, there will be a molecule of B that will move in this direction in order to replace A. So if A moves one direction, B moves the other direction to take its place. So that's what it means. Now, what is diffusion? So yeah, so let's talk about what diffusion is. For example, I have a tube. Let's say there's liquid in this tube for some change, and I put a drop of dye right in the middle. Since it's a dye, I'll change the color of it. Right, so I put a drop of dye in the middle of the liquid. So what's going to happen over time is that the dye is going to move from position of high concentration to low concentration. So basically the dye moves, it starts off here, it starts to diffuse somewhere here, and eventually it gets diffused like throughout the container, and until the concentration of the red dye is uniform throughout the mixture. So if I were to plot a graph, okay, let's plot a graph, why not? So it, okay, that's still red. Let's go with white. Okay, so if I were to draw a graph of the concentration, and I'll call this X, and just to note, this is X. So over time, so initially the concentration of the red dye is very high in the middle, and slowly it starts to diffuse to areas of lower concentration, which means over time the concentration is distributed as such. And again, it keeps distributing until, okay, that was a bad curve. Okay, it keeps distributing until eventually the concentration becomes constant at all points. So what I'm trying to get at here is that diffusion is, at its core, it's the movement of these molecules in this system. So the molecules are moving from one place to another. So that's what diffusion is. So since we've established that for every molecule that goes to one side of A, it is replaced by a molecule of B. So by that same logic, we can say that for every molecule of A that is diffused in one direction, is replaced by a molecule of B that is diffused in the other direction. So that's where this relationship comes from. So yeah, let's use that relationship in order to make our equation even more simpler. Right, let me erase this. Okay, so now what we get is molecular mass of A times diffusive flux of A minus mass fraction of A times molecular mass of A times diffusion flux of A minus molecular mass of B times diffusion flux of A. What I simply did here is replace JB with negative JA. So yeah. And now we can see that the JA term can be factored out. So let's do that right away. JA times molecular mass of A minus mass fraction of A times molecular mass of A minus molecular mass of B. So yeah, so that's what we ended up with. So in conclusion, just keep in mind that we started off with this equation, so we can just bring back the mass diffusion flux right here. So this is the final relationship that we end up with. So what we proved by all these calculations is that the mass diffusion flux of component A is equal to the product of the molar diffusion flux of A and the molecular mass of A minus the mass fraction of A times the molecular mass of A minus the molecular mass of B. So yeah, that's what we ended up with. So I hope you guys learned something from this, and I'll see you in the next one. See ya.